Okay, some molecules we can draw more than one good Lewis structure for. So let's look at ozone, O3. So if we're going to draw a Lewis structure for ozone, we got to connect these three oxygens. We're not going to be doing anything with ring structures in Chem 1A. So we don't want to make a triangle here. We'll leave stuff like that for OChem. So we're just going to put those three in a line, and then we have to ask ourselves, well, how many valence electrons? We have 3 oxygens, they each have 6, so we've got 18 electrons. So there's already 2, 4 from the bonds, 6, 8, 10, 12, 14, 16, 18. So we ran out of dots before we filled up all the octets, so we have to make a double bond. So this is the guy that needs more electrons, and so the next one over, I'm going to take one of his lone pairs and make it a bonding pair to share with the guy on the end. So now this oxygen has 8, and this one has 8, and that one has 8. Okay? Why is it the oxygen on this end that has the double bond? Why not the one on the other end? No good reason, just kind of random because that's how it worked out. So we could draw it like this as well. Try to be more symmetrical than I was yesterday. There's not really any difference there, right? And you might want to argue, well, this isn't different, it's just rotated around. But think of this as being triplets holding hands, right? And this is A, B, and C, right? Well, here C has the double bond with B, and here A has the double bond with B. You try telling 3 triplets that they are the same. They're not. They maybe look exactly the same. They're the same DNA, but they're not the same. This atom is not that atom. So these are 2 different structures. When we study this molecule in nature, we can measure the length of these bonds, and what we find is that the bonds between all of the oxygens are actually the same length. We don't have one double and one single. They're equal. They're in between, kind of like a 1.5 bond. So how does that work? Well, Lewis structure can't do this. Lewis structure is the simplest model that's useful, and it can't handle this. So the way we get around it is we draw both possibilities and put a double-headed arrow between them. And these are called resonance structures. And I remember thinking, resonance, that means like vibrating to me, going back and forth. It must be like jumping back and forth between these. No, it's an average of them, a combination of the structures. Okay? So it's a little bit like breeding dogs. Okay, so you've got German Shepherd father, Retriever mother, and they have a puppy, and the puppy doesn't look exactly like either one of them. It's a combination of the 2, right? We'd say that's a German Retriever or I don't know, a Labrador Golden Shepherd. I don't know. They make stuff up like that all the time. This dog is not vibrating, going back and forth. One day it looks like a German Shepherd, one day it looks like a Golden Retriever. It's always the same thing, but it's a combination. Does that make sense? So we have these 2 resonance structures for ozone. The actual structure is between them. It's an average of them. It is weird. The reason we can't deal with this is that in a Lewis model, electrons are localized. So we have that second bond. It has to be between these 2 or between those 2. It can't be delocalized over the whole molecule. But molecules are not limited by things like that. They don't consult us on how they behave. They just are. And so the electrons are actually delocalized over the entire molecule. And they do that because it lowers the potential energy of the molecule, makes it more stable. It's called resonance stabilization. So we just draw the two structures with a double-headed arrow. Any questions? So let's do an example with resonance. What's the name of this ion? Nitrite. Nitrite. Write a Lewis structure for the nitrite ion. Include resonance structures. Well, we've got a nitrogen and two oxygens. We kind of have to pick how we're going to put those together. Let's put nitrogen in the middle and the oxygens on the outside, because oxygen's more electronegative, so it's usually going to be on the outside. So we'll put a nitrogen in the middle and stick an oxygen on each side. Another kind of good approach is to try to make things symmetrical. It doesn't always work, but it's a good place to start. So then we need electrons. We have two oxygens. They each have 6 valence electrons. We have a nitrogen with 5, and that negative charge means we have to add 1. So I believe that's 18. So now we throw electrons around. We got 2, 4, 6, 8, 10, 12, 14, 16, 18. Ran out of electrons. So we make a double bond. So I'll take a lone pair from the middle and share it with the oxygen. And now, ta-da, we have valence electron, 8 valence electrons for each. This is not mastering chemistry, so I'm drawing the brackets.
So in mastering chemistry, you just don't put it, you just put the negative?
You have to put the negative. You can't do brackets. So what other structure could we draw?
Just put the bond on.
Put the double bond on the other side. The resonance structures are usually going to be just moving a double bond. So here we have a double bond between a nitrogen and an oxygen, and there's a single bond between nitrogen and oxygen. Let's just switch those bonds, because what made that oxygen special? Nothing. So nitrogen, oxygen, oxygen. Now we're going to put the double bond on the right and fill in with our dots. And we still need our brackets and our negative sign. Yes?
Is there ever going to be more than one type of resonance?
There can be, in order to have resonance, you have to have at least 2 structures. There can be more. Yeah.
There can be more resonance though?
Not for this one,
But for others?
but for others, yeah. You can have 3 or 4 resonance structures.
Once you get to that.
There's one on the worksheet that's got 4. Yeah.
So would you have that as
2
2 resonance structures?
resonance structures, yeah.
Basically just mirrored.
Well, in a way, they are mirror images, yeah. So the way I think of it is, okay, so in order for us to have an octet, we're going to need a double bond. But we only need 1. And we've got 2 possible places to put it. These places are equivalent. This is with an oxygen, that's with an oxygen. It doesn't really make any difference. So then both of those are possibilities. And what we find when there are situations like that is that it is an average, and these are each 1.5 bonds. Those electrons are delocalized. So we just indicate this with a double-headed arrow in between. Questions? Other questions? Yes.
Is there going to be more than 2 on the test? Like more than 2 resonance structures?
I don't know what's on the test. There could be.
I'm getting your ideas.
Trying to figure out.
I don't, there are certain things I don't like grading because they're painful to look at, times 60,
Especially when the grades are as bad as ours are.
especially when sometimes they're really, really awful. Correct answers are easy to grade, and blank ones are easy to grade, although they make me sad. It's like, well, let's just write something down. But they are easy to grade. But like I told you, I wasn't going to make you write out a long electron configuration, right? Because it's very tedious to check. And I didn't. I just gave you multiple choice and let you pick one. I put the tedium on you. So drawing Lewis structures, I don't want to look at 4 or 5 resonance structures on an exam. But I'll find a way to find out if you know it or not. Okay, here's formal charge. So formal charges are fictitious charges. This is something we made up. They are a lot like the oxidation states that we talked about earlier. It is the charge that an atom would have if all the bonding electrons were shared equally between the bonded atoms. We calculate this completely ignoring electronegativity. Here's your book's method of doing it. If that makes sense to you, great. I'm not going to go over that. It's a waste of time. So here are the formal charge rules. We've got to have rules, right? The sum of all the formal charges in a neutral molecule must be 0. The sum of all the formal charges in an ion must be equal to the charge on the ion. Small or 0 formal charges are better than large ones. So what we're going to see is that formal charge can help us choose between different Lewis structures. Sometimes we don't have enough information to know which one's best. Formal charges can tell us this one's better because it has lower, smaller formal charges. And then if you have an ion, you cannot avoid formal charges. There's got to be some. And on some molecules, there have to be some as well. So if you can't get them all to 0, then you put the negative formal charge on the more electronegative atom. Okay, so hydrogen cyanide, HCN. We can put this together in 2 different ways. We can put the carbon in the middle, or we could put the nitrogen in the middle. So I'm going to draw this down below so that I can play around with it. So we'll do HCN over there, and we'll do HNC over here. And then number of valence electrons in the molecule, 1 for hydrogen, 4 for carbon, that's 5 total, plus 5 for nitrogen, 10 valence electrons. So we'll stick electrons around. I've got 2, 4, 6, 8, 10. Ran out. So then we have to share some more. So we'll take this one and share in here. And now carbon's good, but the nitrogen's still not good. So I'm going to take this lone pair off of carbon and share it with nitrogen. And then let's do the other one. We're also going to end up with a triple bond and 2 lone pairs. This is how I think of formal charges, not with all this math stuff up here. I think about, okay, we had some atoms, they came together, maybe they formed a partnership, some sort of a business, right? And they were in business together, they pooled their resources, and then the business is going to break up. And they're just going to divide everything equally. So we're looking at cutting the bonds in half. So if I take this, I'm going to cut that bond in half, cut this bond, triple bond in half, cut this bond in half, cut this bond in half. And remember that there's an electron at the end of each bond, right? Okay, so over here, what we're going to do is we're going to compare how many electrons, valence electrons, did hydrogen bring in to this business? 1. And when we split things up, how many does he leave with? 1. So he brought 1, he leaves with 1, net is 0. Ooh, wrong marker. 0. How many electrons does carbon bring? 4. And here, when we break this up, how many does it get? 4. 1, 2, 3, 4. So 4 minus 4 is 0. Nitrogen.
Oh, you're putting.
Yeah.
Thanks. That one is 0. I get lost. I'm so zoomed in, I can't see where I am. That's 0 and this is 0. Thank you. Nitrogen. Nitrogen brings in 5 and leaves with how many? 5. 5 minus 5 is 0. All 0 formal charges. So let's see what this other one looks like. Hydrogen always ends up being 0. He can only make one single bond. When the thing breaks up, he takes half of that bond, his electron back, and he's always 0. Nitrogen. Nitrogen brings in 5 and leaves with how many? 4. So that equals +1. Carbon brought 4, leaves with 5. So that's -1. So we say that this carbon has a formal charge of -1. This nitrogen has a formal charge of +1. Over here, carbon and nitrogen both had formal charges of 0. That tells us this is the correct structure. That's going to be lower in energy. Okay? Assign formal charges to each atom in the 3 resonance forms of N2O. Nitrogen is central, they tell us. Which resonance form is likely to contribute most to the correct structure of N2O? Well, we're told that nitrogen has to be in the middle, so there must be a nitrogen on one side and an oxygen on the other. Doing the valence electrons, we've got 2 times 5 plus 6. For the oxygen, I believe that's 16. We've got 2, 4, 6, 8, 10, 12, 14, 16, ran out of electrons. Got to share some more. Well, let's start sharing. Let's take, that nitrogen in the middle has 8, so we'll get him to share. So now this oxygen's good, the nitrogen in the middle is still good. Nitrogen on the other side, though, only has 6. So nitrogen in the middle needs to share some more. There we go. Everybody's got an octet. It tells us that there's 2 more possibilities. When you're looking at resonance structures, you are not changing the skeletal structure. I can't put the oxygen in the middle and call that a resonance structure. Well, what if instead of 2 double bonds, what if I had a single bond and a triple bond? Oh. So let's put a triple bond there and leave a single bond over here. 2, 4, 6, 8, 10, 12, 14, 16. You can get octets that way. What else could we do? Put the triple bond between the nitrogen and the oxygen. Okay, so 3 resonance structures. We would put arrows, double-headed arrows between them. And we'd say, well, the actual molecule's probably some combination of those. It's not necessarily an even combination, okay? You guys have seen my husband, right? He's Japanese descent, and I'm of Swedish descent. And guess who our kids look more like? They look more like my husband, right? They have dark brown hair and brown eyes. And they go out in the spring and they just glance at the sun and they turn this beautiful golden brown color, and I'm so jealous. And I turn beet red. They look more like him. His genes had more influence on their appearance than mine did. So when we look at the actual molecule here, one of these resonance structures may have more influence on the actual structure, and we can predict which one using formal charges. So we have to do formal charges. So we imagine just taking this partnership apart. We say, well, nitrogen brought 5 valence electrons to the business, and how many would he leave with? 6. 2, 4, 5, 6. So 5 minus 6 is -1. This nitrogen also brought 5 electrons. I'll do him on top. And how many is he leaving with? 4. So 5 minus 4 is +1. And this oxygen brings in 6, and it's leaving with 6, so its formal charge is 0. So calculating formal charges is really not that hard. You just have to remember how to do it. So then let's do this one over here. So nitrogen, I'm not going to do the actual subtracting on the board. I'm just going to talk about it. So nitrogen brings 5. How many does it leave with? 5. So 5 minus 5 is 0. This nitrogen brought in 5. How many does it leave with? 4. 5 minus 4 is +1. Oxygen brought 6, and it's leaving with 7. So that's -1. Notice, this is a neutral molecule. The formal charges, -1, +1, and 0, add up to the overall charge, which is 0. And the same is true here. If they don't add up, then something's wrong with what you did, not with the molecule. What's the formal charge on this nitrogen? It brings 5. It leaves with 7. It's -2. And the nitrogen in the middle? +1. And the oxygen on the end? +1. It brought 6, and it's leaving with 5. So if it broke up and all the bonds were shared equally, this would leave as a +1 ion. This would leave as a +1 ion. This would leave as a -2 ion. That doesn't happen, but that's what we're thinking about. So which one is the worst? This one. They all have a formal charge, and this one's 2. These are better because we've got one that's 0, and the others are only 1s. How do we choose which of these is better? If there's a negative formal charge, it should be on the more electronegative element. Remember, the electronegativity tells us how attractive an atom is for electrons in a bond. So oxygen is more electronegative than nitrogen. So we would expect oxygen to be hogging these electrons, and so this is the best one, this one in the middle. It has the lowest formal charges and the negative formal charges on the oxygen. So do you remember when we were looking at, what color is that? That's the wrong color. So nitrogen and oxygen and their Lewis structures for the atoms. And we said, well, nitrogen likes to make 3 bonds. Here, nitrogen has 3 bonds and a lone pair. It has a formal charge of 0. Oxygen likes to make 2 bonds. Over here, where it's made 2 bonds, it has a formal charge of 0. Over here, where it has 1 bond, it has a -1. Over here, where it has 3, it has +2. If you have the correct number of bonds, then the formal charges are going to be 0. I think it's easier to think about because you don't have to actually do any counting until you get to ones that have a formal charge. You can look at this and say, oh, well, that one's going to be 0 because oxygen likes to have 2 bonds. And this one's going to be 0 because nitrogen likes to have 3 bonds. And these sorts of things become very, very helpful in OChem. Okay, let's do another one. Draw the Lewis structure, including resonance structure for diazo methane, CH2N2. and is telling us that carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charge. Now this one is a little bit tricky because they told us that the carbon was central, but we can still screw it up a bit. So let's do it like this. Let's put carbon and attach the nitrogens. Well, actually, I don't want to do it that way. I'll put the hydrogen here and a nitrogen here and a hydrogen up here and see what we can do. Because that's the first thing that pops into my head when you tell me carbon's central. Put everything else around it, right? How many valence electrons should we be having in this whole structure? 16, that sounds about right. 2 times 5, and 4 for the carbon, and 2 for the hydrogen, 16. So I've already got 2, 4, 6, 8. 10, 12, 14, 16. Don't have enough. The solution is to make multiple bonds. But can I do that? No. Carbon's got 8 valence electrons. It can't go to 10 or 12 valence electrons, so I can't take this lone pair and share it, and carbon doesn't have any lone pairs to share. So what are we going to do?
Just give up.
Give up and go home. Maybe we drew this wrong. So we were told that carbon was the central atom, but maybe the hydrogens aren't on the carbon. Maybe they're supposed to be on the nitrogen. So let's try that. Take that guy off and stick him over here. I don't want to go there, so we're just going to ignore that. And stick this one over here.
Couldn't just leave that hydrogen on the carbon?
I don't want to go there. I don't want to go there leaving the hydrogen on the carbon. So we still don't have octets, but now we could make some double bonds, right? So we'll take a lone pair from this nitrogen and share it with the carbon. So that wasn't enough, right? So take a lone pair. Which lone pair do you want to take? On the other nitrogen. That's kind of what I like to do too. You know, let's just spread things around. Oh, okay. Octets? Yeah? Okay. It says there are other resonance structures. This kind of looks like that last one we did, right? Where we had 2 double bonds, and then we also mixed it up and we did a single and a triple and a single. So carbon, nitrogen, hydrogen, nitrogen, hydrogen over there. So let's put a triple bond here and a single bond over there. And then there were 2 lone pairs, so we'll have to put them here, so that nitrogen has an octet. And then we could do the triple bond on the other side. Except that's not the other side. Like, wait a minute. The other side. And the lone pair's there. These guys look really similar, but they're not exactly the same. So these are resonance structures. And you would indicate that by doing these double-headed arrows. Assign formal charges. Well, let's see if we can pick out the ones that don't have a formal charge, their formal charge is 0. What about the hydrogens? 0. So we don't have to look at those. How many bonds does nitrogen like to make? 3. So here, this nitrogen has 3 bonds and a lone pair. That's going to give it a 0 formal charge. And this nitrogen has 3 bonds and a lone pair, 0 formal charge. Over here, the nitrogen has 4 bonds. There it's got 2, 4, and 2. Those are going to have formal charges. How many bonds does carbon like to make? 4. And carbon is really, really definite about that. Carbon really likes 4 bonds. So here carbon has 4 bonds. All of these are 0 formal charge. Up here, carbon has 4 bonds. Carbon has 4 bonds, 0 formal charges. But the nitrogens have charges, formal charges. So again, what we're doing is we're imagining just disbanding this organization. Nitrogen brought in 5 electrons, and this one's leaving with 4. 5 minus 4, this has an formal charge of +1. And then breaking that up over here, the nitrogen brought 5, leaving with 6. It's leaving with an extra electron. So +1 and -1. So what's the formal charge on this nitrogen going to be? -1. And on this nitrogen, my pointer didn't move. This one, +1. Bless you. Okay? Any questions?
So, sorry, my question took a little long.
That's okay.
Uh,
It's coming back.
in things like that with resonance structures, even though the 2 other resonance structures have funky charges, they're still okay? Well, they're just technically right. Resonance structures, does the element actually often...
That's a good question. So when this one has 0 formal charges and these 2 resonance structures have non-zero formal charges, is it really a combination of all of these, or is this just kind of imaginary? What's up with that? Is that your question?
Mm-hmm.
Well, about all I could expect you to be able to say at this point is that this structure has the most influence on the overall structure. Honestly, if you average all 3 of these, I mean, the average of these 2 is kind of this one, right? So it's probably not distinguishable from this. To really ascertain that, you'd have to study it experimentally. But right now what we're going for is that you be able to identify what resonance is, what structure could have resonance, and using formal charges identify which are the most stable of the resonance structures. Any other questions?